Hey everyone, welcome to the second video from section 8.1 or chapter 8 on numerical methods. So in this video we're going to go into the detail about how we know how far off a numerical method is going to be. So this involves a lot of Taylor approximations, a lot of sort of working things from ground up to figure out how far off we could be at a given step based on how long our time step is and some other properties of our function. So we're going to work through the details there and figure what we actually mean by an order of a method. So you'll hear things say about the Euler's a first order method, the center difference scheme or Hume's method is a second order method. So we're going to talk about what all those words mean, how they all come together, and put things together for how these all work in numerical methods. Let's go ahead and jump on into it. So the first thing you really have to talk about when we're talking about numerical methods is, do they converge? Now, for the stuff we're talking about in this section, we're going to consider a fixed time step or a fixed uniform time step of size h. So what that means is that t1 is going to be t0 plus h. t2 is going to be t1 plus h. They're all going to be the same step size apart, just to make things easier to work with for the methods. So convergence asks the question, do we get the actual solution as h goes to 0? So what I mean by this is, so you're going to take your ODE, you're going to take an initial condition, and you're going to start doing, say, Euler's method, step by step by step by step forward in time. Now what you want to know is that if I send h to 0, does my method give me the actual solution back? Like, do I get closer and closer and closer to the values of the actual solution as h goes to 0? Now, in general, it's not hard to show that this is yes. In general, this is true. And this just comes from the fact that as you send h to 0, your finite differences converge to the derivative. As long as things are bound, which they usually are, you'll get convergence like that. This is just that finite differences converge to derivatives because that is the definition of the derivative. In this case, this question isn't really good enough. The more accurate question, or the more informative question is, how fast do they converge? Because I've been saying all these things about some methods being better than others. What do we mean by that? What we mean by that is how fast they converge to the actual solutions. So what we're going to do, at least for this section for the video I'm going to talk about, is I'm going to ignore the idea of round-off error. Mainly because it's hard to analyze. It depends on your computer, depends on your system, what kind of round-off error you get. The book goes into the details about round-off error, so you can look at that if you want some information about it. But I'm just going to ignore it for the sake of, convenience, and it's hard to talk about anyway. It's really hard to deal with. So really, we want to look at the difference between our actual solution at Tn and the value Yn we get. Phi of Tn and Yn. So phi is the actual solution, and Yn is what we get from our numerical method. So we want to look at how far these guys are apart, because that's really what we care about. Is if we can see how far they are apart in terms of h's, then we're in good shape for knowing how fast we're going to converge. Because we know that Yn is going to converge to phi of Tn as h goes to 0, because that's how we said the convergence works. So the question is how fast. Let's analyze this difference and see what we get. So the first step is to look at what's called local truncation error. And what this really boils down to is, what's the error I make in taking one step forward? So what we're going to do is we're going to assume that at a particular step, we are completely correct. We have landed on the right value and we're at the right spot. So we'll assume that phi of Tn equals Yn and analyze phi of Tn plus 1 minus Yn plus 1. So we're assuming that I'm correct at step n, and I want to look at how far could I be away at step n plus 1. Now what I want to do is I want to look at Taylor approximations. So do a Taylor approximation to phi of Tn plus 1, which we know is phi of Tn plus h because of our consistent step size we've chosen. So phi of Tn plus h, well, what is this in terms of Taylor series? This is phi of Tn plus h phi prime of Tn plus h squared over 2 phi double prime of Tn star, where Tn star is some point in Tn to Tn plus h. This is just Taylor's theorem with remainder. And I get that set up there. Now we can plug some things in, right? So let me rewrite this one more time. So phi of Tn plus 1 equals what? It equals phi of Tn plus h. Now what is phi prime? Phi prime at Tn is just f, right? Because my ODE is dy dt equals f. This is just f of Tn yn plus h squared over 2 phi double prime of Tn star. Now, if we're looking at just our normal Euler's method, what do I get for y of n plus 1? Well, for y of n plus 1, my normal Euler's method tells me I'm going to get yn plus h f of Tn yn is exactly how I calculate my next step. So if I look at the difference between these two equations, what do I see? Well, I know we assumed phi of Tn was yn, and that also let us make this assumption here. So what this all tells me is that my difference between phi of Tn plus 1 and yn plus 1 is basically is h squared over 2 phi double prime of Tn star, which if things are bounded nicely, this is basically some constant times h squared, where m is just an upper bound for phi double prime. For, I guess 2m is an upper bound for phi double prime. Just the function as a whole. So how big could this function be? It's some continuous function. I can just bound it. And if I bound it, I know that I'm going to be within m times h squared at my next step. So what this tells me, in terms of words, is that my local error is of order h squared. And that just came from the fact that I got an h squared out of this calculation here. It's bounded by some constant. That constant might be huge, but it is of order h squared. Now, what we actually care about is step 2, is the global error. So say I care about the value at some later time. So let's say I start at t0 and want to know how far off I am at t0 plus 1, taking steps of size h. Now, I know my local error is h squared, so at each step, I make an error of order h squared. Well, how many steps do I need to get from t0 to t0 plus 1? Well, if each step is of size h, I need 1 over h steps to get there. I need 1 over h steps to get from t0 to t0 plus 1. So my overall error is mh squared times 1 over h, which is m times h. So this is a first order method because I have just an h here, not an h squared. And so Euler's method is a first order method because of the h to the 1 that shows up here. Now how we could use this idea is that what happens if I cut my step size in half? What can I expect to see for my error? Well, if I cut h in half, my error bound is proportional to h. So I expect to see that I would be half as far away from my solution. I would make half as much of an error if I cut my h in half. I would expect to have be half as far away as I would for the first time than if I do it the second time, if I cut it in half. If I cut h in a quarter, I'd expect my error bound to be quartered, which means I should be about 4 times as close to the solution. This sort of thing only works for first order methods. For second order methods, if I had an h squared there, if I cut it in half, I would expect to be 4 times closer. I would expect to have a quarter less error bound by cutting my step size in half. This is why these higher order methods are useful, because they give you bigger improvements for smaller increases in numerical computation. Because if I cut h in half, I have to take twice as many steps, which means the computer is doing twice as many calculations. So just cutting the error in half for twice as many calculations isn't really that great. Cutting the error by 16-fold for twice as many calculations is a lot better. And that's where the last video we're going to talk about, we're going to cut a fourth order methods, because fourth order methods means if I cut the step size in half, my error goes down by a factor of 16, which actually in that case is probably worth it. All right, so that's the main points I wanted to hit in this video. What are error bounds? How do we get them? We get them from Taylor series. And what do we mean when we say a method's first order? And that's that the error goes as multiples of h, as opposed to h squared for second order methods, and what it means in terms of error bounds when you change step size. All right, thanks for watching. Next video, we'll move on and we'll talk a little bit more about the improved Euler or Hume's method and how you can improve your numerical results just using a couple of changes. All right, thanks for watching, and I'll see you in the next one.